Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing linked list topic and the pattern was linked list with stack or using hash map. So in this pattern today we will solve the next question, which is remove nodes from linked list. So let's read the problem statement. It says we will be given a linked list, head of the linked list, and we have to remove every node which has a node with a greater value anywhere to the right side. Okay, so we have to remove all such nodes which has a greater value in upcoming nodes. So as you can see, for 5, towards its left, do we have any node which is greater than 5? Yes, for 5, 13 is there, although 8 is also there, but 13 is the node which is just greater also, so we don't need to worry about 8 or something else. Once we found any one node which is greater than 5, then we can say, hey, delete 5. 5 is not needed. Similarly, we will go for 2. Now for 2, what is the next greater element here? 13. So again, 13 is there. Yes. So 2 is also not needed. So we have to delete all such elements which has a greater value towards its right side. Okay. Now let's see the constraint. The constraint says the number of nodes will be minimum 1 and maximum 10 power 5. Okay, why we read the constraint? Because the minimum and maximum values will help us to write the base case and to optimize our code. As a minimum number of node is 1 given, so for sure if head is null, return null, we don't need to write, correct? Second is maximum number of nodes is 10 power 5. So if anyhow we are going or we are thinking to write the code in O of n square time complexity, then 10 power 5 and 10 power 5 together becomes 10 power 10. And you know, because you have seen our time and space complexity video, that beyond 10 power 8 it's very risky, and for sure 10 power 9 and 10 though will give TLE for sure. So hence we have to optimize this, means we have to write in linear solution. Now the node value is given from 1 to 10 power 5. Why this is required? See, a single node value can be 10 power 5 and there are n number of nodes. So if there is anything related to summation of node values, then we have to think, because integer can hold value up to 10 power 9, and beyond that if you have to sum it up, then you have to convert this into long format. But here summation is not required, so we don't need to think for that format changing. I hope you understood. Now let's see here. Here the linked list has been given and we have to check key for 5, do we have any greater node here? So how it is possible? Suppose you don't know how to iterate in the linked list. Let's see the very brute force approach. First, we will start a current pointer just to iterate and read the values, and I hope this much though you all are aware of in the linked list. Okay. Now what we will do, in a list or array we will store the values of linked list. 5, 2, 13, 3 and 8. Now, can I say ki I have my list values here? Now I have to check ki do these numbers present at different indexes has a greater number towards its right side, and how it is possible. Suppose I want to find for I, means I is equal to 0, means suppose I want to find for 5. So for 5, can I say ki start a pointer towards its next and start running from this index till last index until we find a greater value. If we don't find, no problem. So can I say I will start my j pointer from I plus 1? Now I'll keep on running my j pointer and I will check ki hey, 2 is greater than 5? No. 13 is greater than 5? Yes. So it means if we have found any such value at index j for index I which is greater than index I, for sure I can say I don't need it. So what I will do now, I will create an answer array, and in this I will not put 5, means ith value I will not put. So once I found array of j greater than array of I can say hey, need to delete I because we have found a greater number. So stop, break, and now move your I ahead. So what we will do, j will vanish, I will move ahead. Now I have to look for 2. Again I will start my j from I plus 1, correct? Now again I will check, hey, array of j, is this greater than array of I? It will say yes it is, means for 2 also there is a node which is greater than I, means I needs to be deleted, means can I say in my answer I will not store 2 also? Okay. Now again j will vanish and I will move ahead, correct? Now for I, again j will start from I plus 1. It will say ki hey, array of j which is 3, is it greater than 13? No, it's not. Again we'll move ahead. Hey, now Is 8 greater than 13? No, it's not. Again, we'll move ahead and we'll see, hey, we are out of index. Means for ith value, we have not found anything. Okay, then this is my correct answer. So how we can say? We can run a flag also. Okay, ki if for any I, jth value was greater, then make the flag true. Correct? And break that while loop. And after coming outside, if the flag was true, then you can not, like, you can skip inserting this number in the answer. Correct? And here in this case, j, like, there was no such condition where our array of j was greater than array of I. So if it was not true, then flag has not become true. Correct? Means initially, if we have initialized our flag with false, so this is still false. Now after coming outside of the while loop, correct, if our flag is false, it means we have not found any such value. So in our answer array, we will simply add answer.add array of I. That's it. So what we will do, we will insert 13 here. Now again j will get vanish and I we will move ahead to find for 3. Now for 3, j we will insert here, like start from here. Again we'll check, is this array of j 8 is greater than array of I, which is 3? Yes, it is. Now for 3 also we have to delete, means this also, for this flag will become true, and if flag is true, we will not insert array of I in the answer. Okay. Now again the j will get vanish and I will start from here. Okay. Now for this j we will start, but j will not get started because it is out of index. So for this again the flag has not become true, means flag is false. Flag is false, then array of I we will insert here, and that's it. Now at the end, this is the answer array we have. So we will create a new linked list starting with a dummy node. We will connect 13 and 8. Correct? Dummy is here, and at the end we will return dummy.next. So 13 and 8 will get returned, and that's what expected answer also. But what is the time and space complexity here? First O of n to iterate, read the value and put in the array. Then further O of n square. For every ith, you run the j from 0 to last, na? Although it gets stopped at 13. But what if for 5 we had 2, 1, 1, 1. Then to for I, j will keep on iterating, na, until it hits a greater value or out of index. So can I say the time complexity will be O of n square? Because for every I, j is running from I plus 1 till last. So O of n square. And what was the value of n? If you know, 10 power 5. So n square will become 10 power 10. TLE. Is it acceptable? No, it's not. So hence, although it was brute force code, but because of the constraint, it's not acceptable. So what is the different approach? And one more reason. Here in the previous solution, we have stored the value in somewhere else in the array, correct? Means what if that is not allowed? Means storing the values is not allowed. You have to play with the linked list only. Then to for sure this was not acceptable. Then what is the second approach? And for that you have to understand and play with linked list. So if you are following our playlist, for sure you would have understood how to play with the nodes and when to apply that array list, storing the node value in the array list logic, and when not to. So in this case, now let's play with the nodes itself. Okay, how can we play with the nodes? So can I say if I am standing at here, so I'll like mark my current here, and for 5 obviously I have to find the nodes which will be sitting from current.next till last, correct? So can I say I will start my 2 pointer, let me raise this. I can say ki hey, this will be my current, let's say, and I will start my let's say current.next, I will start my temporary from here. Okay, now my task is only to check if my temporary dot value is greater than current, then I can say delete current, correct? So I'll check, hey, is my current like temporary value greater than current? No, it's not. So just keep moving this temporary ahead. Now I'll check, hey, is my temporary value greater than current? Yes, it is. Means can I say I have to delete this current? But if you have understood how to delete the node in the linked list, you know this, that to delete this node, there should be something at previous, correct? Yes, yes. Otherwise, see, it is possible to delete anyhow. How? In this case, it will become delete a node which is present at the first position. Then you have to move your head ahead. But why to make it complex when it is very easy and you know how? To create a dummy node, yes, and connect this. Okay, so we'll create a dummy node and we will connect this. Okay, and we'll start a previous pointer. Why? Because you know, like dummy we start, but dummy we never move, correct? Because head is going to be manipulated. It might be. So previous pointer we are going to move. Dummy will stick to the same position, and at the end, if required, we'll return dummy.next as a head, new head. Yes. So now what we will do, if we have to delete this, you know what to do. Previous.next connect to current.next. Very simple. Then we can say yes, current has been deleted. Yes. So guys, can I say, like for every node we have to calculate the next greater. So can I say current will move till, now don't say ki second last or like this. See, you can write like that. But don't you think ki let's move till null only na? Yeah, I can say that. So while my current, can I write ki while my current not is equal to null. Okay, keep doing this. Now wherever my current is sitting, for sure my temporary will start from current dot next. Done. And now I will need a flag, let's say delete, which will be of type boolean. Initially it will be false. Correct. Now we have to check, keep running the temp ahead until the temp becomes null. So can I say while my temp not null, okay, in this keep running, but first check ki is my temp value greater than current value. If it is, then for sure mark the flag true and break the for loop. Can I say this? What I said. Temporary, initially temporary was here. Can I say? Now is this temporary greater than current value? No, it is not. Then what do you think? You should move current ahead or you should move temp ahead? For sure temp ahead, because you are looking for a next value which is greater than 5. So if not, then just move your temp ahead. Temp is equal to temp.next. That's it. Now your temp will move to this position. Again you will go, is my temp null? No, it's not null. Is my temp value greater than current value? 13 is greater than 5. Yes, it is. Then what you have to do? Obviously delete, like flag will become true and the while loop will break. So can I say after coming outside the while loop, I have to delete this current. And how can I delete the current? By moving previous dot next to current dot next. Correct? So we'll write previous dot next is equal to current dot next, and we can say yes, current has been deleted. But this while loop though could have been broken because of the temporary is equal to null also, na? Yes, it's not sure for sure key because of this break loop. It might happen you would have not find, like temporary has not find anything. So temporary has become null and now the while loop has broken. So how can you say delete this? It is only possible if your flag is true, correct? So what we will do, we will add this line of code only when if our flag which is here deleted is true, correct? Yes, else we will see when we will get that condition. Now can I say this? So this will get connected to this. So for sure we'll remove this and previous dot next will connect to this. Although like 5 is still connected, but it's not needed. Now what do you think? Should we move current ahead? Yes, because now for 2 we have to find, right? So either this if case will run or else case will run. We will come at this line and we'll say, hey current, please move yourself. Means current is equal to current dot next. Done. Okay. Now current will move ahead to this. Again, we will come in the same while loop. We'll say, hey, is my current null? No, it's not null. Now what? Next. So again for current, new temp should start from current dot next. Okay. So temp is started. Now again the new flag is false. Now while my temp is null. Now for 2 we have to find what is the next greater element. Okay. So again for 2 also 13 will become the next greater element. Again flag is true, correct, and will break. Coming outside we'll say, hey, is the deleted flag true? Yes. Then previous dot next connect to current dot next, means now the previous will connect to 3. Can I say, sorry, 13. So this will also get deleted and this will get connected to this. So by default, can I say ki if I like read from here, so 0, 13 and now this has been deleted. So again you know that again you have to move your current ahead. Okay, current null, no, it's not null. Again you have to start your temp from current dot null. Done. Now what we have to do is is this temp value is greater than this? No, it's not. So if it is not, temp will move ahead. Correct? Yes. Yes. Now, again, 8, is this greater? No, it's not. So now in this case, what will happen? See, in this case, I can say that temp will point to null, correct? And now this while loop will break because of temp null, correct? So now if you will come here, it will say deleted is equal to true. No, the flag is not true. Means for 13 you have not found anything. So can I say this is my valid node? Yes. So what do you think? Like going forward, this is for sure not going to delete. And in the whole node, what was the node which was for sure granted? Can I say my previous node? Because previous was pointing to that and previous next we were changing. So previous is not going to be deleted. So as we have not found anything, any greater node for 13, so I can say I can mark this previous, correct? So that's what in the else case, we have to write keep previous is equal to current, because this current is not supposed to be deleted. So what will happen? Previous will come to this, correct? Now again current will move ahead, so current will move ahead to current.next. Now for 3 we will start our temp from here, but here in this case we will find what? Yes, temp value is greater, so flag will become true, and if flag is true, previous.next will get connected to current.next. So what is my new previous? 13. So 13 next will get connected to? Yes. So 13 next will get connected to 8. Now again we'll move our current ahead. See, we can stop our current here also. Why? Because for 8 we know ki for sure there is no node which is greater than this. So we can stop here also. Where? Ki if our current.next not null. Now if you are thinking about the base case, ki what if current become null? No, it won't be. Why? Because for sure the number of nodes is given already, it will be minimum 1. So if it is minimum 1, for sure initially for this, if you will check what is my current.next, which is null. So for the one node, we don't need to delete anything and we need to return then and there, correct? So we can put like this also. So here we will stop. Now if you will read from dummy, what is the node? 0, 13, 8. Now what are we supposed to return? Are we supposed to return dummy or dummy.next? Dummy.next, yes. And that was also the one of the reason we always prefer to create a dummy node, so that the tracking of the new head will become easy. Otherwise you have to keep in if else loop. Okay, so we can do this code, yes. At the end we'll simply return dummy.next. But what is the time complexity? Although we have not created any extra space to store and then manipulate, we have played with linked list. Okay, the condition is valid, but still what is the time complexity? Because you can see for every current you are running your temporary from first, like second position to last position. Can I say? For every current, temporary is going to start from current.next to last. So it's nearly O of n square only, na? For every ith you are running your j from I plus 1 till last. N square is valid for this case, kya? No. Why? Because n is already 10 power 5 and n square will become 10 power 10, and you know beyond 10 power 8 it's not safe, and for sure 10 power 9, 10 power 10 so will give TLE. So we can write the code, but because of the TLE it won't be accepted. So here is a code which we have discussed. Okay, now let's try to run the code. Definitely it will run, but when it comes to submitting the code it will give TLE. Why? Because of the constraint 10 power 5. Okay, for sure it will give you TLE as expected. Yes. So now we have learned using the extra space complexity, using like playing with the nodes, but we did in n square. Can we do this in O of n? Let's see. Don't you think it's about next greater element only? And whenever we have to think for next greater element, if you are following our playlist, yes, then there we have used stack data structure, because stack data structure helps us to reduce the time complexity from O of n square to n, correct? Remember? So we have to use a similar concept here as well. Okay, so like if you are thinking it is about next greater element towards right, then you are wrong. Why? Because see, here we don't need to print key what is the next greater element to it. Then to we always start from right side. Remember? But it is about deleting the same node. So don't you think if we will start from the left side, 5, we will store in the stack. Now next time 2, stored in the stack. Now next time 13, 13 found. Go in the stack and check, are these nodes greater than 13? Yes. Then we need to pop it. Because for 2, we can say we have found greater node towards its right side. Yes, very easy. So we will start our traversal from current. Okay. If we have nothing in the stack till now, so we'll write ki while our current not null. Okay. Now in the stack we will push current. Correct. Done. So initially we'll check ki hey, where is my current? Okay. So current we will push in the stack. Now we will move our current ahead. So we have to write current is equal to current dot next. Now in this time for 2, don't you think we should look back in the stack? Correct. So can I write ki while my stack is not empty? Yes. And along with that, yes, 2 will say yes, stack is not empty. But what is the popping condition? Ki stack dot peak needs to be smaller than current element. Correct. So what we'll write ki if stack dot peak dot value. Why? Because in the stack we have stored nodes. So with value we can compare ki dot value if it is greater than current dot value. If it is greater, then for sure we need to pop. So what we will write? Stack dot pop. Done. So for 2 we will check ki is it smaller? No, it's not. So we'll come out stack dot push. Again we will push to second node, which is 2, and now we will move our current ahead at 13. Now for 13 it will go check ki hey, is my stack empty? No, it's not. Now is my stack dot peak dot value, which is 2, is it smaller than 13? Yes. So we will pop. Okay. Now that's why we have written while loop ki keep on popping until you have all the smaller numbers. So again for 13 it will check yes it is. So again pop both. So now I can say my stack will become empty, and at the end 13 will get inserted, and we will move our current ahead at 3. Correct. Now again we'll go ahead, current not null, yes it's not null. Is my stack not empty? Yes it's not empty. Is the value of stack peak is smaller? No, it's not. So don't pop. Come outside, push yourself. So 3 will get inserted. Now we will move our current ahead at 8, let's say. Okay. Now again we'll check ki is this null? No. Is my stack empty? No, it's not empty. Is the stack dot top value is smaller? Yes. So we need to pop it. So let's pop it. Again for 13 also we'll check is this smaller than 8? No, it's not. So now inner while loop will stop, and coming outside we will insert our current node in the linked list, like stack, sorry. So 8 will get inserted. Now again we'll move our current ahead, and now the current will become null, and we can say yes, come outside the while loop. Done. So in the stack what we have? We have 8, we have 13. Okay. So we have to return this only, na? Can I say that? Correct. So what we will do? We will iterate in the stack one by one. So we will pick elements. First 13 was there and then 8 was there, right? So one by one we'll pick. Like we will run the for each loop in this. So we'll pick, and first we'll start from a dummy node, let's say 0. To its next we will connect this node, which is 13, and to its next we will connect the next node, which is 8, and that's it. And at the end, which is this is dummy, right? So at the end we will return dummy dot next. So 13 and 8 will be our answer. What is the time complexity? See, we have iterated the current from starting till last. And if you are thinking about this while loop, ki O of n and O of n, no, it's not. Why? Because if you see, for any current, for this you have not popped, for this you have not popped, for this you have popped. How many times you have popped? 1, 2. Okay, done. Now when you went here, not popped. When you went here, you popped. So don't you think, in the worst case, suppose this is, the value is 15. So in the worst case, you will come, you will pop this and you will pop this. Are you going to pop this and this again? No, because only one time you will pop. So altogether, this while loop and this while loop is going to take 2n time complexity in the worst case. Worst case means 5, 4, 3, 2 and suppose 6. 5 you will insert. 4 will check, is it smaller? No. 4 you will insert. 3 you will insert. 2 you will insert. Now 6 comes and 6 will say, hey, all are smaller than me, na? Pop everything. So O of n you went towards right side, and further O of n to pop everything, means O of 2n only. So the time complexity will be O of 2n, but space will be O of n. Why? Because in the worst case, you will end up pushing every node in the stack. Correct? Extra space complexity is there, but time complexity you have reduced to linear. So can we write the code for this? So here is the code what we have discussed. First we'll make a stack and we'll start our current pointer until our current pointer is null and the while stack is not empty and the previous value, if it is smaller, then pop. This logic is nothing but if you have solved those questions in the stack playlist, key next greater element, next smaller element towards left and right, then you can understand this code. Okay, there we have already discussed in depth. Now after coming outside, I understood one thing, ki we have in the stack, we have only those nodes which are needed to be connected. So we'll make a new node dummy and start iterating with the tail pointer. So now we will iterate every node in the stack one by one. We are not popping. So don't think we are popping so top element will come out. No, we are iterating in the stack one by one, and in the tail dot next, which is starting from dummy. See, we are starting from dummy, right? So this is dummy, let's say. So this is tail also. So in the tail dot next, we will pick this. We're not popping. We are iterating one by one. Okay. So first 13 will come. So to its next 13 will get inserted, and to its next 8 will get inserted. That's what we are doing. And at the end, tail dot, like dummy, because tail is going to move ahead, right? Tail will come here. One time tail will come here, but we have to return this. So that's why we are not moving dummy ahead. So at the end, dummy dot next will be our answer. So see. So now after this, we can return dummy dot next. Now, do you think tail dot next, because whenever we connect any nodes like 13, then in 13 dot next 8, then we supposed to connect its next to null. Remember? Because what if any other nodes are connected? But don't you think in this case, either it is 8, 1, 2, anything, towards its next, no node is going to be greater than this. So for sure, this node, which is at the top of the stack, is nothing but the last node of the linked list. So its next is already equal to null. So we don't need to connect its next to null. Can I say this? So we can remove this line of code. Still it will run. Yes. So let's run the code. And once passed, let's try to submit this. So this was the code in Java. And if you understood the approach, here is the code in Python, and here is the code in C++ with a similar approach, okay, where space is O of n, time is also linear, okay. Now after this, we will see the different approach where we will prefer not to use extra space complexity as well. Means, if possible, let's play with the nodes itself. So now the approach which we are going to discuss is the most optimized approach, because this will be linear solution also and without using any extra space complexity. And this logic is called reverse plus maximum so far logic. And what is this? Let's see. So the idea is very simple. Don't you think we have to delete like previous numbers? That is why we created a node and we kept a previous pointer. Correct. So what do you think? If we are coming from right side, what will happen? We are at 8. For sure, we don't need to delete it because this is going to stay. Why? Because for 8, there is no node towards right side. Okay. Now we'll come here. And one more thing. As of now, what is the maximum value? You have to keep a track of it. Okay. At starting, when your current was here, you can update your max. So what's your max? Max is 8. Done. Now your current will be at 3. So you can say ki, hey, is my current value is smaller than maximum? Yes. Yes. Okay. But one more thing, guys. Stay here. Okay. And let's ask by current dot next only. Very simple. I am at here. Maximum is 8. Is my current dot next dot value is smaller than maximum value? Yes, it is. Means for sure we have to delete. And in this case, we don't need to keep a track of previous pointer and anything, because here though we have to keep track towards right side, and from right side only the number is saying ki, hey, I have found a number which is greater than you in future. So for sure, let's delete yourself. And now to delete, you just need to connect current dot next to current dot next dot next. Very simple. So what is the condition? Ki if your current dot next dot value is lesser than max value, then connect your current dot next to current dot next, which is nothing but deletion of that node. Can I say that? Yes. Or else we will write. Now can I say I have to move my current behind? But how is it possible in the normal linked list? No. If we want to traverse back, for sure we have to reverse it. So before applying all these conditions, we have to reverse it. Then only we can come from right side to left side. Can I say that? Yes. So let's say we have reversed it. Now to for sure we can move our current behind. Now again, can I say after disconnection of this, 3 is no more. Okay. So let's delete this now. Okay. Where was our current previously before deleting 3? Current was at 8, then only 3 got deleted na, by connecting current dot next to this. Okay. Now, do you think we should move our current ahead? Because what if it was 5? Then to for sure this current dot next we have to connect to this, because I will say ki, hey, for 5 also I am greater, correct? So we have to keep on doing this in a while loop. Can I say? While, but until when? While my current not null, yes. And one more thing. Why one more thing? Because for any current you are checking current dot next value. So for this next should also exist. Can I say that? Very simple. Current dot next not null. Then keep on doing this. Correct? Now again we'll go ahead. Current not null. Yes, it's not null. Next not null. Yes, it's not null. Current dot next value. Is this smaller than maximum till now? No, it's not. So now can I say this is correct? 8 is also going to stay and 13 is also going to stay. Now we can say move my current ahead in else case. So in else case, what do you think, what should we write? For sure, current is equal to current dot next, move ahead. And one more thing, 13 is still there and not gets deleted because 13 was greater than 8 for sure. So now the current maximum is current or the previous. Can I say current? So the max value we have to update with current dot value. And that's it. Again we'll go above. Now as we have moved our current behind, so current is pointing to 13. Now we'll say, is my current null? It's not null. Current dot next is null. No, it's not null. Is my current dot value, is this smaller than max value? Max is 13. Correct? Let's update this 13. So yes, then current dot next we have to connect to this. So can I say this will get disconnected and connected to 5, means 2 gets deleted. Again we will again check, is my current still there? Yes. Is my current dot next still there? Yes. Now is my current dot next value 5 is smaller than max value, which is 13? No, it's not. So we have to delete it. Again current dot next connect to next. So when you reverse this, na, this was connected to null. So now 13 will get connected to null. Correct? Now again in the while loop you will check current null. No, it's not null. Current dot next null. Yes, it's null. So now we will come out of this. Okay. So after reversal, this was not there. Now after coming outside the while loop, I can say ki I am ready with the linked list. Correct? This got deleted na, 5 got deleted. So I am ready with the linked list, but I don't have a track of 8. So before moving your current ahead, this was your new head, right? So keep saved your new head, and after coming outside the while loop, just return your head, and that's it. So what's the time complexity for this case? First, so you have reversed. Correct? You have reversed. Okay, so O of n to reverse. Now O of n to traverse and delete everything. Correct? Now do you think 8 and 13 was your answer, or 13 or 8 was your answer? Yes. So further can I say nearly O of n? Correct? So further O of n to reverse the final linked list so that it will become 13 and 8. Why I said? So in the worst case, O of 2n for the reversal and O of n is for iteration and deletion. So O of 3n total, which is linear only. Now space complexity, if we talk about, we have not used any extra space. We have played with the same linked list. So if the modification of linked list is allowed and space is very costly, space is not allowed, then go with this approach. But if the space is not so costly and modification is also not allowed, then go with the stack solution. So I hope you understood all 3-4 approaches we have discussed. So can we write the code for this? Here is the code we have discussed. First we will call the reverse function with the same head. How to reverse a linked list we have already discussed in our previous video. I'll attach the link somewhere here. If you still have doubt in reversal of linked list, then for sure the prerequisite will be that video. Now after reversal, we will start our current with the new head. Okay, means the last node. Can I say this 8? Okay. Now the same logic which we have discussed until our current null or current dot next null. If the current dot next value is less than max, max will start with the current value, which is 8. If it is less than, then delete, means connect its next to dot next, or else move your current ahead and set your max value with the new current value. Okay, and at the end again you have to reverse the linked list and the new head you have to return. So this is the simple code. I hope, I feel this is the most easiest one if you know how to reverse the code. Okay, and if also manipulation is allowed. So let's submit this code, and this code we have written without using extra space complexity. Although we have to return the linked list, correct? So this is going to take time, space complexity, but we have not used it like any extra, like in case of stack or array list we have used, okay? So this is the code in Java, and here is the code in Python if you are from Python background with a similar approach, and here is the code in C++ if you are from C++ background with a similar approach. So if you understood all 3-4 approaches, when to apply what with the proper notes, then for sure you can go in the sheet and mark the next question also as done. So I hope you all would have understood. If yes, please do mention in the comment section, and if you have any doubt, that too feel free to mention that in the comment. And if you like the video and understood all the approaches, hit the like button and subscribe the channel if not yet subscribed. And that's it. Let's meet in another video with some more interesting questions, topics and patterns. Till then, keep learning, take care of yourself and your family too.